Okay, let's bring everything together with the concept of the posterior. So the posterior is the end result of Bayesian reasoning. It tells us what we believe now after combining our prior belief, the likelihood being how well the data supports each possible belief. Now this is our updated belief, our best estimate of what's true after factoring in the new evidence. Now to recap Bayes' theorem in full, it is the posterior equals the likelihood times the prior divided by the evidence, where the prior is our starting point. Then the likelihood comes from data. The evidence is just a normalizing constant. So it's a constant here. And the posterior is our new belief adjusted for what we've seen. Now, what is a normalizing constant? Well, a normalizing constant is a number you use to adjust or scale a set of values so that they form a valid probability distribution, meaning that the values add up to 1. So as an example, let's say I've got a bunch of numbers that relate to probabilities, but they're not quite probabilities yet. I need to scale them so they make sense. And that's what the normalizing constant does. It's called normalizing, and normalize means to make standard or consistent. So in probability, that means making sure all your probabilities will add up to 1. And now the posterior is our new belief, adjusted by what we've seen. Now everything we've talked about and everything we've covered so far comes together here. Now let's use a quick example again with a coin toss. We say we believe a coin is fair. That's our prior 50-50. So there's 50% chance heads, 50% chance tails. But after flipping it 10 times, we see 8 heads, and that's our data. So that's the actual data we have. The likelihood suggests that 8 heads in 10 flips is more likely if the coin is not fair. So our posterior will shift, maybe towards 70% or 80% heads, depending on how strong our prior was and what the data showed. This is Bayesian thinking in action. It adjusts beliefs based on outcomes. Now, the posterior is more than just a single number. It's a full distribution. It shows which values are most likely, how uncertain we are about them, and where the credible intervals lie. In Bayesian models, they give us more than just a point estimate. They give us confidence in our estimates and help us to make more informed decisions based on uncertainty. So now that we've covered the posterior, the next step is to talk about credible intervals, the Bayesian version of confidence intervals, basically. So we'll break this down and break down the difference between these two and how to explain them clearly, especially to non-statistical audiences or those that aren't statistics professors. Okay, we'll see you in the next video.